going to look at some different types of factorising. The first one I'm going to look at is to factorise this number. I've got Dean's blocks here with 168. So I've got 168, and what I'm going to do with this 168 is to divide it by 12, which we might see written like this. And then 168 divided by 12 will often be rewritten with this strange symbolism here, this bus stop division. What does this actually mean? Well, I'm going to factorise 168, and I'm told that one of the factors is 12. So, with my Dean's blocks, if I can make one of the lengths of a rectangle equal to 12, which I can, take my Dean's blocks here, we have a rectangle where one of the lengths is 12. I had 168 here, and I've just removed 120. What I'm left with here is 48. That's why these numbers appear here in this column here. We've got a story of what's happening physically. If I can take my Dean's blocks and make a perfect rectangle, then I will have factorised. So, taking the rest of my Dean's blocks, with this example, I am able to make a perfect rectangle, and I can arrange the Dean's blocks perfectly like this. And this might be how I start off with students, well, ones that can be factorised. Now, I had 48 here, I've removed 48, and I'm left with nothing. And now the other length is 14. So, 168 divided by 12 is 14. 168, it's all here, 168 divided by 12 is equal to 14. 168 divided by 14 is equal to 12. What if instead of having some numbers, I have an expression? Let's say, for example, x squared plus 5x plus 6. Is this any more difficult? Well, if we take an algebra tile and we say this length here is x and this length is x, this is going to be x squared. And an algebra tile where this length is x and this is 1, then that's got an area of x. So I need 5x. So I've got x squared plus 5x, and then some little 1 by 1s to give me my 6. And I have x squared plus 5x plus 6. We know that making a perfect rectangle, an area of a perfect rectangle, will show me its factors. So I've got x squared plus 5x plus 6, x squared plus 5x plus 6, and can I make a perfect rectangle with this? Well, yeah, sure. So rearranging my algebra tiles into a perfect rectangle, I can see the structure of this multiplication, this factorization that's going on here. This is still x squared plus 5x plus 6, and now one of the lengths is x plus 3, and the other length is x plus 2. So x squared plus 5x plus 6 is the same as x plus 2 multiplied by x plus 3. X squared plus 5x plus 6 divided by x plus 2 is going to be x plus 3, and x squared plus 5x plus 6 divided by x plus 3 will be x plus 2. And the entire structure is there. Often what we see happening with students is they're then told that if the coefficient of x squared is not 1, so we have a number in front of x squared, that this will be a more difficult question, which is of course nonsense. Suppose I had something like 2x squared plus 5x plus 2. So let's do this with my algebra tiles. I need to get this time 2x squared plus 5x plus 2. And the exercise is exactly the same. Can I create a perfect rectangle with my algebra tiles? Well, let's have a look. So I've got 2x squared, and this time I've got 5x. So let's look at taking our x's and arranging those into a way where I get a perfect rectangle, filling in my ones there. And this is 2x squared plus 5x plus 6. It's the exact same materials, 2x squared plus 5x plus 6. And one of its lengths is 2x plus 1. So we've got 2x plus 1. And its other length is x plus 2. So it factorises to 2x squared plus 5x plus 2 factorises to 2x plus 1, x plus 2. But it's also showing us that 2x plus 2x squared plus 5x plus 2 divided by 2x plus 1 is going to be equal to x plus 2. 2x squared plus 5x plus 2 divided by x plus 2 is going to be 2x plus 1. 2x plus 1 multiplied by x plus 2 will be 2x squared plus 5x plus 2. If we take another example, suppose we look at something, for example, x squared plus 4x plus 3. And this time what we ask the students to do is to complete the square. Again, this is often considered to be a higher level, but is no more taxing. So we have 2x squared plus 4x plus 3. We do have that here. Complete the square. Why is completing the square referred to as completing the square? You often see this taught abstractly by people saying we half the coefficient of x and we do a squaring. Well, actually, can we make a square? Well, let's have a look. We can almost make a square. We can almost make a perfect square. And this square would be x plus 2. So we have this square, x plus 2 squared. And there's one missing. So x squared plus 4x plus 3 is the same as x plus 2 all squared minus 1. And we've completed the square. Suppose we want to look at a polynomial, let's say x squared plus 5x plus 8. And we want to divide it by another, let's say x plus 2. Now we know we've got x squared plus 5x plus 8, x squared plus 5x and plus 8 here that we've got, x squared plus 5x plus 8. And we know that one of the factors, just like 168 divided by 12 earlier, one of the factors will be x plus 2. So if I can make a length of x plus 2, so I've got x plus 2 as one of the lengths here, x plus 2. Now I've just removed x plus 2, and over here I have remaining 3x plus 8. So we've got 3x plus 8 remaining, and at the moment I've got x plus 2 multiplied by x. So I'd have an x in here. Now, if I can make a rectangle, I will factorize. But look what happens on this example. So when I make my rectangle, I can't quite finish it off. So I've just removed 3x plus 6. 3x plus 6 over here. And I'm left with remaining 2. So x squared plus 5x plus 8 divided by x plus 2 is x plus 3, remainder 2.